So we kind of reviewed everything we know about ionic compounds. It's between a cation and an anion. It's got a charge of 0. We have to always let the cation go first. It gets to keep its name, and the anion goes second, and it ends in IDE. So let's do a couple practice here. Let's say that I want the chemical formula for tungsten sulfide. Okay, tungsten sulfide. Tungsten is not one that we use very often, but tungsten is number 74. It's down here in the middle. Okay, so we've got to first figure out what's its symbol and what's its charge. Okay, tungsten has a charge of what? 6, right? It's a W, and it has a +6 charge. Bless you. Sulfide is our anion, and it has a what charge? -2. Okay, so can you see the ratio on how they're going to fit together? Maybe yes, maybe no, okay? But either way, we can use our crisscross method, and we ignore the plus and the minus. We crisscross this down to be W2S6. But can I leave it like that? I have to reduce them because they are both reducible by what number? They're reducible by 2. So I need to reduce it down to be WS3. That would be my finished and complete ionic formula for tungsten sulfide. Okay? How many of you saw right away that I need 3 of those to pair with tungsten? That works perfectly, right? If you know that I've got a +6 and a -2, I know I'm going to need 3 of them. Just write it that way, right off the bat. But if you want to do the crisscross method, that's fine. You just have to make sure you reduce it at the end. Okay? All right. What would be the written name for this molecule? ZnF2. I want you to give me the written name for that molecule. Okay, the written name. Does the written name care how many of each element there are? It doesn't matter. It makes no difference. So the written name for this is just going to be what? Zinc fluoride. Zinc fluoride, not fluorine, fluoride. It makes no difference how many of each of them we used. It doesn't make a difference what their charges were, right? Naming it, writing the actual physical name is super easy because you just name the cation, then name the anion, and that's it, right? So very simple there. Okay, any questions with that? All right, are we ready to make it a little bit more difficult? A little bit more intense? Okay, we're going to look at what are called polyatomic ions. Oops. Polyatomic ions. Okay, what do you think the prefix poly, what does that mean? The prefix poly means what? Multiple, many, right? There are a lot of ways to describe it. But a polyatomic ion is an ion with multiple atoms. That's it, right? An ion with multiple atoms. And we have a whole list of polyatomic ions up here in the box on your periodic table of ions. Take a look at that box. Okay? Take a look at that box. They are all a molecule, a compound of some sort that is not neutral, that has a charge. And the reason that molecule has a charge is because of the number of electrons that each of those brings to the table. Okay, so it has to do with how those molecules are bonded. It leaves it with a charge. And so we're able to treat most of those polyatomic ions. Would you say most of those polyatomic ions are cations or anions? Look at your box right here. They're mostly what? They're mostly anions, right? They mostly have a negative charge. So we're going to treat them just like we do an anion, except polyatomic anions, they don't change their name. They just keep. Okay, so polyatomic ions just keep their name. Okay, so I want you to look at Let's find one right here called carbonate. Do you see carbonate? What's the formula for carbonate? CO3, and that has a -2 charge. That means this whole compound right here, CO3 as a whole, has a -2 charge. So we're going to treat this just like we would, sulfide that has a -2 charge. Right? We're going to treat that polyatomic ion as its own thing, right? It has an identity of being CO3, which means if it is CO3, we never change that 3, right? That 3 is off limits in terms of ever being reduced down because carbonate's identity is to be CO3. Does that kind of make sense? So we're never gonna adjust that subscript. The same would be true for any subscript here as a part of our polyatomic ion, right? That is its identity, right? Carbonate identity is CO3 with a -2 charge. Phosphate, try to find phosphate. These are in alphabetical order here. So phosphate is PO4 -3. Okay, that's its identity. So we will never adjust that 4. Because if we adjust the 4, it's not phosphate anymore. Now it's phosphite or something else. Okay? So let's do a couple practice with polyatomic ions. And even before we get there, I want you to look at a couple examples. I want you to look at, let's see, ClO3 -1 and ClO2 -1. This name is chlorate, and this name is chlorite. Okay, take a look at those two, and then I'm going to give you another example. SO4 -2 is sulfate, and SO3 -2 is sulfite. Do we see a pattern? I want you to look at a pattern here between the eights and the ites. Okay? To go from chlorate to chlorite, what happened? We changed the subscripts, but what specifically? Yeah, Nathan, what do you think? What happened?
It is of less, has less.
One less of what? One less oxygen, right? One less oxygen. So yes, our subscript changed. We have one less oxygen. What about from sulfate to sulfite? What do we have? One less oxygen. So let me think through this pattern here. That means if I know any polyatomic ion that ends in 8, I also know the ite version of that polyatomic ion. It just is subtracting one less oxygen. So to go from 8 to ite within our polyatomic ions, it means we have one less oxygen atom. Okay, does our charge change when we do that? It does not. The charge stays the same. So we keep that charge, but if we want to go from 8 to ite, we have one less oxygen. So tell me this. What would be the formula then for phosphite? Phosphite. What's the formula for phosphite? Okay, how would I go? I'm going to go find what on this in the box? I'm going to go find phosphate, and then I'm going to take away one oxygen. So what do you think the formula for phosphite might be? PO3 -3. Right? Do you see how that works? So not only do we know everything in the box, we also know some of the extra ones. We know some extra polyatomic ions. In the past, I've had us memorize some of these polyatomic ions. I don't think I'm going to do that this year, but it's going to be really important that you do become familiar with them because it's going to save you a lot of time, right? If I automatically know what carbonate's structure is or formula is. It's going to save me a lot of time when I go to do my naming, okay? So we want to make sure we're comfortable here. Any polyatomic ion that ends in ate or ite, we have to find it in the box, right? We won't find phosphate on the periodic table. This is just regular phosphide. So we have to understand the difference here, okay? So let's look at the difference. P by itself, -3 is called phosphide. PO3 -3 is called phosphite. And PO4 -3 is called phosphate. So you see how just these tiny differences make a big difference in the structure of our molecule. So we can't make mistakes with that, right? We have to make sure we're really paying attention to the ending of our anion. Okay, do you know what I'm saying there? Really, really careful with that. These ones have to come out of the box. This one would come right off the periodic table of ions, right? Ide is just it by itself. There's a couple exceptions to that, but not too many. Okay? Let's try actually building some formulas now, okay? Remember, these guys get to keep their name. Phosphate, phosphite, they get to keep their regular name, okay? So, let's try some examples. Give me the formula for calcium nitrate. Calcium nitrate. So, will nitrate be found on the table or in the box? Table or box? Box, because it ends in ate, right? Nitrate has to come from the box. So let's find calcium. Calcium is our cation. It has a +2 charge. Nitrate is NO, what? NO3. And it just says minus, but we assume that's a -1, right? If it just has a minus sign, we're putting a 1 there with it, okay? Do we see how they're going to have to fit together? Or do you like the crisscross better? How many of you can you see right away how they're going to have to fit together? Okay, so if they're going to fit together, we need 2 nitrates. Would we agree with that? Okay, so here's how it works. I would have to put CaNO3, and I need 2 of those nitrates, which means I need to put nitrate in parentheses with a 2 on the outside to show that I need 2 of everything that's inside that box. Everything that's inside that parentheses, I need 2 of the nitrate. Okay? I can't put a 2 outside of it without parentheses. That doesn't make any sense. Okay? We have to put it in parentheses anytime we need more than 1 of a polyatomic ion. So let's write that out. Use parentheses anytime we need more than 1 of a polyatomic ion. Okay, anytime we need more than 1 of a polyatomic ion, we have to use parentheses. Okay, what if you didn't see right away how they fit together? I could use the crisscross method. And I'd bring the 2 down here. I'd bring a 1 down here, which is exactly what we have. A 1 and a 2, right? Crisscross method still works even with polyatomic ions. Okay?
But would it be wrong if I didn't use the parentheses?
It would be wrong if you don't use the parentheses. Yep, we use parentheses anytime we have more than 1. Okay, so let's try this one. Magnesium phosphate. Magnesium phosphate. Okay, magnesium's charge is +2. Phosphate, is phosphate just a P? No, it's got to come out of the box. So phosphate is PO4 -3. Okay, this one's a little trickier to see how they're going to fit together because you've got a +2 and a +3. So this one, the crisscross might be better suited. So we would ignore the plus and the minus. We bring down the 3, We bring down the 2. That leaves us with Mg3, PO4, 2. Right? PO4 goes in parentheses because that is phosphate, and we're saying we need 2 phosphates to make it neutral. And so I put that in parentheses there. Can I reduce these down? No, right? Because the 4 is part of phosphate's identity. So I don't ever touch that. That is non-negotiable. Okay, so that 4 is off limits. The only thing I'm looking at to reduce is the 3 and the 2. And I can't do that, right? 3 and 2 are not reducible by the same number, same whole number. Okay, how do we feel about that? Okay, let's try a few more here. Let's do... Oops, sorry. Let's do potassium chlorite. Potassium chlorite. All right, potassium is K, and it has a +1 charge. I'm going to look for chlorite in the box. Is it in there? It is. If it wasn't, I could just look for chlorate and take away an oxygen, but it is. So ClO2 -1. Do I need to bother crisscrossing here? No, because my charges are the same, right? So I know they're going to fit together 1 to 1. So my compound just becomes KClO2. Do I need to put parentheses around it? No. I don't, because I don't need more than one of them. Do I have any charges listed in my final formula? No. I do not, right? Sometimes people just do this. No, right? That's not a final formula. Final formula has to be the ratios intact with no charges. So this would be our final formula there. Okay? All right, why don't we try this one? Try this one on your own. I want the written formula I want the chemical formula for barium hydroxide. Hydroxide, that's a new one. And it's going to be in the box as well. Hydroxide, even though it ends in IDE, it's going to be a polyatomic ion. Okay, so barium hydroxide, I want the formula.
Why is it
OH, and it's a -1. So I'm going to crisscross, bring the 2 down, bring the 1 down. That leaves me with BaOH2. Did we remember to put the OH in parentheses?
Yep.
Okay, here's the difference, especially with hydroxide, it makes such a difference. If I did not put them in parentheses, if I had forgotten, this says BaOH2. That means that I only need 2 hydrogens. And it means I don't need 2 O's. But that's not the case, right? I need 2 of this molecule, which means I need 2 O and 2 H. So the parentheses are super, super important. So this is no good, right? We have to have parentheses because I needed more than one of my polyatomic ion. Okay? Looking at the elements in the middle. I want you to take a look at these transition metals. What do you notice about some of them? The transition metals in the middle. What do you notice about some of them? What do you notice? Do they all have one single charge? Some of them have multiple charges, and they are given with a Roman numeral next to them. Do you know what a Roman numeral is? Right? How many does that represent? 2, right? That represents a 2. So you see that those charges are represented with Roman numerals. These transition metals, these cations in the middle, have some flexibility with what their charge can be. And so we use Roman numerals to help us determine which version of, manganese or iron or cobalt, nickel, which version of those cations we're dealing with. So the Roman numeral tells us the charge of the cation. Okay? So Roman numeral, write this word down. It tells us the charge of the cation. Do you see a Roman numeral happening with any anion? Do you see a Roman numeral for any charges that are negative? No, they all work with the cation. Okay? So it's simple when we go from words to formula. It's a little trickier when we go backwards. So let's try some words to formula first. Let's say that I wanted the chemical formula for manganese 2 oxide. Manganese 2 oxide. So manganese is not the same as magnesium. Some of us run into that problem, but manganese is right over here, number 25. And the Roman numeral 2 tells us that manganese, Mn, will have a charge of +2. That's all that it's telling us, right? It's giving us an extra piece of information. And so, say it again. Well, you look at the Roman numeral that they gave you. That's the charge right there. So you can do it without looking at the periodic table. Oxide is -2. So how will those fit together? M, N, O. Right? If you did the crisscross, ignore the plus minus, bring the 2 down, you would be MN2O2. But what would we have to do there? We would need to reduce them down so that it comes out to be MNO. Right? Do you understand the difference between that and this?
Yeah.
This would mean nitrogen. There's not even an element with just an M, but we can't do that, right? We got to make sure our lowercase and uppercase look different. So Roman numeral is not so bad when we go from words to formula, but going backward is a little bit trickier. Okay, let's try another one of these and then we'll go backward. All right, give me the formula for, for cobalt 3 hydroxide. Cobalt 3 hydroxide. Do you remember what hydroxide is? It's going to come out of the box. That's a polyatomic ion. So it comes out of the box. Cobalt 3 hydroxide. So this 3 tells us that cobalt has a +3 charge. That's what that Roman numeral tells us. It automatically tells us the charge of our cation.
So I don't even really need to look at.
You don't have to look up the charge for cobalt because it's already telling me that. Yeah. And then hydroxide, I needed to maybe look up, but that's a -1. So I can crisscross or I can just put it together. But I should end up with CO. Do I need parentheses?
Yes.
Yes, COOH3. If I just have this, COOH3, that means I only want 3 hydrogens, but really I need 3 of the OHs. Do we feel good about going from words to formula?
Yeah.
Okay, I'm going to have you try the opposite one here on your own. So let's say that I want the written name of CuCl2. I want the written name for that one. Let's see if you can figure it out on your own. CuCl2.
I just do chloride.
Okay, what do you think, Hannah?
Copper 3 chloride?
Copper. Hannah says 3.
Oh, I meant 2.
I did
2. Okay, so Hannah says 2. Copper 2 chloride. Does anyone have anything different? Did anyone choose copper 1?
That's the one I had.
Okay. So let's figure out what. A couple people put copper 1 chloride. We've got to figure out which version it is. Okay? The way that we can tell, there's 2 ways we can go about it. Okay? 2 ways. We can reverse the crisscross. That would leave us with Cu +2 and Cl -1. I can check, is this chloride's normal charge? Yes or no?
Yes.
It is, which means that the +2 is correct. So this is our correct one. Copper 2 chloride. Another way we could look at it is if we just look at CuCl2, I know automatically that chloride is -1. So that means this whole side needs to be -2, which copper has to be +2, right? We're doing the same check system here, but that's what we're looking at. If it was copper 1 chloride, our formula would have just been CuCl. They would have fit together perfectly because the anion charge never changes. So I'm always kind of checking it with my anion. Okay? All right, let's try another one here. Let's say that I want the formal name. I want the written name for this one. SNO2. I want the full written name. SN is number 50. Okay, so let's go back and check. I think the easiest way to check is actually not to reverse the crisscross. I think the easiest way to check is just to use oxygen. So what do we know oxide's normal charge is? -2, and there are 2 of them, which means I have a -4 over here. So what does tin have to be? Has to be +4. So I agree. I think tin 4 oxide is correct. But the difference is this molecule has been reduced, right? If we would have done the reverse crisscross, SNO2, I bring that up, I would bring a 1 up, -2, I'm sorry, +2 and -1. I know that's not oxide's normal charge. Oxide would have had to been -2, which makes this +4. Okay, so we can check it, I think, with our negative charges. A little bit easier than reversing the crisscross. I think the reverse crisscross makes it a little bit tricky.
How do you do your method?
Okay, so if this is SNO2, oxide's charge never changes. So if oxide is a -2 and there are 2 of them present, that gives me a total of -4 on this side, right? My oxide gives me a total of -4. There's only 1 tin atom, so that means it has to be +4. Okay. All right, let's try one where we see a little bit more reduction happening here. So let's see. Give me the... All right, give me that formula. Give me the written name for that one. I know it's going to be iron phosphate, but do I need to include a Roman numeral? Yes, right? Would I need to include a Roman numeral if my cation was like calcium or potassium? I only have to include a Roman numeral if it's one that has multiple charges. So I don't include a Roman numeral otherwise. But what should my Roman numeral be here? Iron what? Phosphate. Iron 3 phosphate. Does everyone else agree with that? Iron 3 phosphate. I know that because I know phosphate is -3. And these two fit together 1 to 1, which means iron had to be +3. Right? It has to be +3, right? If we did the crisscross, we would have reduced them down. So our final has to be +3.
Why would oxygen not be included in the answer?
Say it again.
Why would oxygen not be?
Oh, okay, because PO4 has the identity of phosphate, right? That is phosphate, and it's in the box. Does that make sense? Okay, first one, I want... Oops. Okay, so the first one, you're going to give me the formula, and then the second two, you're going to give me the written name. Silver carbonate. Leia, do you want to tell me what you had? Okay, good. I think that's right, except I think you don't have to have the parentheses. That's the only difference, because I don't need more than one of those. But good. Ag2CO3. Perfect. Agreed? Okay, what about the next one? Someone want to volunteer that one? PD is palladium. Yeah, what do you think, Nathan?
Palladium to sulfide.
Palladium to sulfide. I would agree. Good, because they fit together 1 to 1. I know sulfide is a -2, so palladium has to be a +2. So perfect, I agree. Good. All right, what about on the last one? Yeah, what do you think, Hannah?
Chromium to sulfate.
Chromium to sulfate. Yeah, I inadvertently gave you 2 of them that were +2s there, but yes. Chromium to sulfate. I know sulfate coming out of the box is a -2 charge, so chromium has to be paired with that as a +2.